Assalamu alaikum. I welcome you all to another lecture on power electronics. In the today's class, we will discuss about the turn-on characteristics of a MOSFET, and we will see how these turn-on characteristics are important to understand and to design a gate driver circuit for any given MOSFET. So let's start with the class here. So MOSFET has some capacitances due to the depletion layer and the stray capacitances. So typically we have three type of capacitances in a given MOSFET. The first capacitance is between the gate to source. The second one is between the gate to the drain, and the third one is from the drain to the source here. These are written as or abbreviated as the CGS, CDS, and the CTS here. And this cross-sectional view of MOSFET structure, it clearly depicts that we have the CGS available here, we have the CDS, and we have the CGD available here. Notice that all these three capacitances are not responsible and do not have a direct impact on the switching speed. Rather, we have the first two capacitances, which is the gate to source and the gate to drain, which are responsible for the impact on the switching speed, whereas this capacitance CG, it is mainly used in the case of the snubber design of any power electronic circuit here. So in order to understand the impact of these capacitances, we first need to create an electrical equivalent model of a MOSFET, and that model must be able to depict the performance of a MOSFET, whether it is in a cutoff region or in the ohmic region or in the active region here. So as we can see here, this is a graph which is plotted between the drain to source voltage and the drain current ID, and it is plotted based on different values of the gate to source applied voltage here. Now this graph is taken from a data sheet which is for this n channel power MOSFET NTB 685860NL. It is able to block 60 volt and able to conduct 220 ampere while having an RDS on of maximum equals to 3 milliohm here. So that means that if we are at this region, which is the cutoff region, it is the cutoff region, we are holding the voltage, that is the MOSFET is in the blocking state. And if we want to take it into the conduction mode, that is the MOSFET is going to turn on, then it has to traverse between this area until it reaches this area which is known as the ohmic region here. We have now three areas. The first one is a cutoff region, another one is an ohmic region, and each of these three can be attributed in terms of two equivalent circuits here. So the first circuit is this of a circuit which is characterized by a current, a voltage controlled current source, where the drain current ID flowing through this MOSFET. Let me draw this thing here. So this is the current ID here. So this drain current ID is now dependent as a function of the gate to source applied voltage, which we apply between the gate terminal and the source terminal here. Now, if you notice here that this is a function of this VDS, so therefore this ID is equal to 0 whenever the gate to source voltage is less than the threshold voltage of that given MOSFET. For any given data sheet, there is a threshold voltage which is usually between 1 to 3 volt, and sometimes it is equal to 4 volt, below which the transistor will remain in this cutoff region. However, beyond this thing, this ID is a function of a transconductance parameter multiplied by the VGS minus the VGS threshold, and this is used to identify, and this is used to model the MOSFET in this region, which is known as an, we call this an active region here. Now this transconductance parameter is an important parameter, and it is usually given in the data sheets. For example, here we have in this data sheet we have a graph which represents the drain current as a function of the gate to source voltage, whereas we have set this VDS to be greater than equal to 10 volt here. So here you can see there are different curves available here for different junction temperature values. For example, the one in the middle, it represents the junction temperature of 25 degrees centigrade. Then we have a junction temperature of 125 degrees centigrade, and the third one, which is this one, which is let me highlight here. This is at minus 55 degrees centigrade here. So these models are exponential. However, we can apply simple linearized modeling techniques here. So once we linearize this given thing, then the slope of this linear model can be attributed in terms of a function which is known as the GFS. Usually this value of GFS is also given in the datasheet of a given MOSFET, and we will understand how to use these GFS while when to design a given MOSFET circuit here. So this GFS is the rate is the difference between, it is taken between the 2 points, and that represents the change in the drain to source current, and this on the other side it represents the change in the drain to source voltage here. So, the VDS here is something which can be attributed, and therefore this given model is valid only for the cutoff and the active region model. However, when we are operating in the ohmic region model, we cannot use this model, and therefore we need to have another model for that purpose, and that is represented in terms of the of this given model here. Now, in this given model, as you can see here, we have the same drain to source and the gate terminals available here. We have the two capacitances, which are the CGD and CGS, and we have another parameter which is known as an RDS on. RDS on is the drain to source resistance when the MOSFET is in an on state mode, and this model is only valid for the ohmic region. And remember that the value of the drain current flowing through a given MOSFET, it depends on the on the VDS as well. So before we move ahead, let me reiterate this thing, that this RDS on is not something which is constant. However, after you exceed a value of VGS, it becomes more or less constant, thereby creating these linear regions, and thereby we call it as an ohmic region here. So as you can see here, it has a high value below the threshold voltage. After it crosses the threshold voltage at this junction temperature of 25 degrees centigrade and at 20 ampere, you can see here that this slope is almost constant. That is, there will be a very small change in the value of the RDS on. Okay, so the next question here is that do we have these capacitances which are represented as CGD, CGS, and the CDS? Are these the resistances which are constant, or they vary with time? So we have the CGS, which is the gate to source capacitance. It approximately is constant, and it is independent of the applied voltage. However, the gate to drain capacitance CGD, it has two distinct values which are important to understand, and we attribute them as the CGD1 and CGD2 values here. So CGD2 values, the gate to drain capacitance values, it happens because of the distinct change in the gate to source voltage and the drain to source voltage. So let me elaborate this thing further. Suppose that I have this given MOSFET here, and this MOSFET is in an off state. In an off state, if we measure the voltage here between the drain and the source, this VDS shall be holding a voltage which is equal to this VCC here, if the transistor is in off state. And if this VDS is high, if the VDS is high, as you can see here, then we will attribute the value of the CGD as CGD1. However, once we are trying in an operation to turn on this MOSFET, it will have a VDS, a point of VDS, because once it will go into the conduction mode, the VDS will slowly go to a point where it will act as a short circuit, whereas the current IDS will begin to rise here. So based on these two values, when we have this VDS less than or equal to the VGS, which is the gate to source applied voltage, then the capacitance CGD will reach to this value, which is attributed as CGD2 here. So these two values are now a function of the gate applied gate voltage here. Now the capacitances which we encounter in a given MOSFET data sheet, there are three different type of capacitances given in the electrical specifications of any MOSFET. These are the input capacitance CISS, which is the sum of the capacitance as seen from the input side. It is the sum of the CGD and the gate to source capacitance here. Then we have an output capacitance COSS. This COSS is a sum of the capacitances between the gate to drain and the drain to source. And then we have a reverse transfer capacitor CRSS, which is the basically the gate to drain capacitance here, which is only this capacitance. So based on these three values of the capacitance, once we understand how a given MOSFET behaves, at a later stage, once we have this understanding with us, we can then go for the charge enclosed in these capacitances and the time required to charge and discharge these parasitic and depletion layer capacitances, and thereby we will be able to identify the key parameters which are required to design a given gate driver circuit here. So that's what we are trying to establish here. So the next question is, are these capacitances fixed? And we have seen that they do have some impact on they do have some impact by the amount of the gate to source voltage. So the gate to drain capacitance CGD varies with applied voltage, and therefore we can see that the CISS and COSS and CRSS, they do have an impact on the with respect to the applied drain to source voltage. So as the MOSFET goes into the connection mode, the VDS, which is the drain to source voltage, as it is increased, their values become more or less constant. As this VDS is low, they have variation as seen by the datasheet values here. So let us understand how a given MOSFET works. So for a given MOSFET, what we have assumed here is that we have a converter circuit here, which is actually a buck converter, and this buck converter is having a highly, is operating in a CCM mode, and therefore this I naught represents the output current. Which this is a freewheeling diode. This freewheeling diode will help this current source to circulate the current during which the time this MOSFET is in an off-state mode. So here you can see that this is the MOSFET. It's an open circuit here. That means it is basically now in an off state. It is in an off state here. So now it is holding whatever is this VD available here. So now what is happening here, that as soon as we apply the gating signal, we cannot have an instantaneous change from its off state to an on state. Rather, what will happen, that this VGS will slowly rise to it will slowly, for example, if this is the final value of this VGG, it will slowly rise like this. During the first mod on, we have the gating current, because as you can see here that this gating current shall have an instantaneous change in the system, because we have the capacitances available across this network, and therefore the capacitances do not oppose any change in the current, and therefore you can see that this gate current immediately rises to a higher value here. Later on, what will happen, that the current which is going here, it will bifurcate into these two capacitances, and it will have its root something like this. At this particular point, this current and this I naught, they will combine, they will use this freewheeling diode system, after which here this current which was flowing through CGD1, it will flow through this side, and it will come back here, and it will have its complete circuit here. Now this rise in the VGS, it will have a time constant tau, that is equal to the RG into the CGS plus the CGD1 here. So this is the time constant here, and if we continue with this slope, then this light green color impact shows the trajectory of this waveform if we continue on this given path. Notice here that because this MOSFET is in an off state, therefore we are actually operating at this particular point here, because it is holding a higher voltage between the drain to source, and therefore the capacitance which will be used to find out the time constant during this duration is CGD1. It is not the CGD2 here. So with respect to this thing, this is the once you have understood this circuit, you should know that these are the two graphs for the gating current and the gate to source threshold up till the threshold voltage, and we call this as the delay time for an on state. During this on state, we still have no share of this output current flowing through this MOSFET. The VD, which is the voltage here. Here we are measuring the VD here. This VD is also having its value. It is still not into the conduction mode. Once we overcome this stage, then we have the VD. We have this VGS. Once it crosses the threshold voltage of that MOSFET, what will happen is that as it moves on to the threshold mode, the transistor moves on into the active region. During the active region, we have the drain current, and consequently, as you can see here, that this drain current starts to flow here as shown by this dependent current source. So we have a linear rise in the drain current. But however, in the active region, we also have the VDS available. So VDS is not a lower value, and therefore you can see that the VDS is still at this at the same value here. On the other side, for the gate current, the gate current becomes it comes to a lower value, while this VGS is still rising here. We call this as the T rise time, or the rise time for this thing. So now we have the two distinct operating times. The first one is the delay time, the second one is the rise time here, and this is the equivalent circuit here. Now once we are in this after this equivalent circuit, we have finished with this rise time, then is the fall in the voltage, and it will be in two different shape. The transistor moves in this state. The VGS is having its trajectory, and it is settled here. And during this given time, we have we can observe the Miller plateau here, and we have this TFE1 available here. This is the total current here. As you can see, that now this current is the drain current ID, and this diode is not conducting here, and therefore this I naught shall be flowing through this ID here. So as you can see here, that this ID has raised up to an current which is equal to this I naught here. But still we have this VGS, it is VDS is coming down, but it is still yet not in the ohmic region. So after that, in the second phase here, we have this VDS. It goes on to a very low state value, which is corresponding to whatever is the voltage in the ohmic region. This ID is fixed here, and because the voltage across the VDS is very low, and therefore we are right now in the falling voltage 2 state. And after this given state, you can see that this dependent current source is now replaced by an RDS on, because this RDS on represents the behavior of a MOSFET in an ohmic region here. So after that we have we can safely say that after surpassing these 1, this 2, this 3, and these 4 states, we are finally in VDS on mode here. So once we and this particular time, this duration is known as, this is the Miller plateau here. And after this, the gate to source voltage, it will rise up to the value which is the maximum applied voltage here. And this time constant tau is equal to RG into CGS plus CGD plus CGD2 here. And why? Because it is CGD2, because right now at this after this instant, we have the VDS which comes to a lower value here, and that complies with the earlier slide where I have explained that the gate to drain capacitance is dependent heavily on the amount on the VDS. Higher the VDS, lower is the value of CGD, and lower is the value of DS, the higher will be the value of the CGD here. Seen that after transitioning from these 4 states, the MOSFET comes into a halt state. In this particular example, we have assumed that the diode is an ideal diode, and therefore there is no reverse recovery time required for the turning off of this freewheeling diode. What if we have the freewheeling diode with some reverse recovery time? So that reverse recovery time TRR, which is characterized by this area, this peak reverse recovery time IRR, peak recovery current IRR, will also be reflected into this waveform, and that is shown in this next slide here. So as you can see here, now if we have a diode which is not an ideal diode, and therefore it exhibits the reverse recovery time and hence the reverse recovery current, then that current will also be reflected onto this transistor MOSFET performance during the turn on characteristics here. And that is that instead of having only this I naught plus IRR will also flow through through this MOSFET circuit, but that will not be in the ohmic region. Rather, it will happen in those transitioning instants where the MOSFET is operating in the active region. So as you can see here, after the rise time, we have this TFV1 where the voltage starts to fall here. In this particular time instant, we have, this is the drain current that it has to achieve. Rather than having its value straight set at this ID, it will go on to this value such that it will have the it will take into account the IRR that will also flow in addition to the I naught available here. And once, because this IRR has to come in an end after we replenish the time TRR for that for that freewheeling diode. So once it is off, this thing will vanish and the diode will set to its rated drain current value, which is designed for that given circuit here. So other than that, if you see these type of peaks here, that peaks are only because of the reverse recovery time of the given diode here. Now these circuits that we have explained so far, it represents the on-time characteristics of a MOSFET. The off-state characteristics of a MOSFET are more or less the same. They just have some some inversion here in terms of these nomenclature values. However, it is more or less the same, and therefore we may not be able to discuss them in this class. So in the next class, we will inshallah move on to the more understanding of this MOSFET in terms of the gate driver circuit. So thank you very much. Take care. Allah Hafiz.